Yes, so as I mentioned, we are focusing on a problem of stress because cancer patients frequently experience negative emotions, and stress is one of them, as well as fear for future. And those emotions hinder not only their well-being, but also they correlate with reduced treatment compliance and increase their risk of mortality. So as a part of Capable project, we want to support cancer patients both with the treatment adherence, but also with developing positive health habits that in the long term should help them to become more emotionally resilient. And we will do that through virtual coach that is accessed via mobile app and also a smartwatch. And the virtual coach will be able to provide activity suggestions to the cancer patients. And each of the activity suggestions should become a positive health habit on some point. So when we're talking about developing habits, we looked into the literature from psychology on how actually the habits are developed. And there is a model from Fogg that says that for a patient to perform a behavior, there have to be three components present. One is a motivation to perform the activity. The other one is the ability. So the activity has to be easy enough for them to perform. And the last one is a trigger. So something that will remind the patient to perform the target activity. And in this work, we assume that patients are actually motivated to increase their own well-being. And we found an activity which is simple enough that every cancer patient could perform it. And this activity has been shown in literature to reduce stress, and this is breathing exercise. So the main challenge in this work, and in the next slide that we will be talking about, is to designing a trigger that will deliver the reminder at the most suitable time for the patient. We suggest to approach this problem from using both the wearable device and machine learning model. And we want to prompt the patient, at least we hypothesize this would be a good time, at the point they are more stressed, because this is the point where they need the most of the intervention. So we consider developing personalized stress detector first to detect the moments when they are in the point of increased physiological arousal, which kind of signifies their stress. And there is lots of work done on detecting stress using ECG, for example, or respiratory rate. But here we're interested specifically in detecting stress from blood volume pulse. Why from blood volume pulse? Mainly because it can be captured with the kind of wearable devices, which are commercially available. And also has a nice ability that while you're performing rhythmic breathing, it alters its pattern. So you can later on check if the patients indeed actually perform the activity. Okay, so you can validate if that it changed. So first of all, we wanted to evaluate if what we are proposing with the stress detector actually can work on raw blood volume pulse. So we asked this question, can it perform equally well as the previous methods, which kind of used feature extracted from various signals, but more specifically from VP, or it can't. So we didn't know that at that point. And then later on, we asked a question, can we do even better if these models are being personalized to the patient? So to start developing the model and perform the evaluation, we used publicly available VESAT dataset. It was a very nice dataset captured in experimental conditions from 15 subjects. And there were 3 different experimental conditions. One was neutral, stress, and amusement. It was interesting for us to look on the stress and amusement because there are both high arousal states, but they're really differ in the experience of the stress. One is negative and the other positive. So we wanted to discriminate between those 2 states too. And the patients were also, participants in the VESA dataset also filled a questionnaire, which kind of reflected the perceived stress levels, if you like. So this is the data, and the model, as kind of shown on the pictures before, it's very simplistic 1D CNN model. And unlike prior methods applied to this specific data set, we don't use handcrafted features, but input instead straightforward, like 60-second long part of a signal into the model, and then try to classify whether it represents stress or non-stress situation. So to test our two hypotheses, or kind of two research questions, we designed two experiments. So first I will describe a little bit about the first one. So kind of to directly compare our stress detector to the previous work, we used the same experimental design, which is leave one out, meaning that we trained on the whole population and tested on one withheld subject. For this, maybe you can see more detail in the paper about all the parameter setting, but maybe one important thing to mention to balance between the samples from the various conditions, we had to vary the step size because, for example, the amusement condition was 20 minutes and 6 minutes was stress. So kind of during training to make sure that we can train properly model, we adjusted the step size for the extraction of the signal. So we have a balanced training examples. So let's see what happened. So we managed to achieve equally good, if not actually slightly better performance on both stress versus non-stress classification using row BVP. And also on a free class condition, stress, baseline, and amusement. So that's great. But the thing which we observed is that there is large variation between performance between patients. So here I'm quoting for two-class problem, like varied between 71 to 98 for stress classification. The one which is plotted is actually from the free class problem. So we wondered why is the case. Maybe we are just better in detecting people who are really, really stressed, but those who are moderately stressed, we are not necessarily detecting their stress. So to kind of investigate this hypothesis, we plotted the stress performance level from our free class problem classifier versus the perceived worry as reported by participants. But even though you can see here kind of a weak trend line, it has not been significant. So actually this is not true what we thought. Instead, what was happening, our stress detector was just way better in classifying stress when the signal was very erratic. So we wonder, okay, maybe we can do better. Clearly, we should be able to detect when people are very, very stressed or worried. So we created the second experiment in which we are trying to personalize the models. So similar as in the first one, the model was trained first on 13 participants, 14 validation, and the last testing. But for the testing, we kind of split the data set into two, and part of the patient's signal was used for testing, and the other part we used for fine-tuning of the population model. And it was like really small number of examples. And we wondered whether this kind of fine-tuning, simple fine-tuning will help us to achieve better stress classification performance. And when we looked at the performance, we have here results for both population model as before and personalized model. And in two-class problem, we have a slight increase in performance, which is good enough, but in terms of free class problems, we have quite a bit much more impressive performance improvement, because for the majority of the participants in the study, the personalization actually helped. So we have here a few conclusions from this stress detection study. First of all, yes, we can detect stress from raw dot volume pools, but there is a large variation in the appearance of the signal between the participants. So personalization can be helpful. And here we've shown that kind of even very simple fine-tuning on very small number of annotated samples, so shows kind of encouraging improvements in classification performance. But just to mention, the stress detector is, of course, just a part of the larger system. So its performance is important, but to evaluate the whole system, we would want to compare the timing of prompts, the one of being done through detection of a stress point with random prompting. And this is the only way we can figure out which really patients, it's better to prompt the patient at the point that they are stressed, or maybe this is actually not the good timing. And as mentioned already before, we can validate it through looking again on the changes on blood volume pools, whether the activity has been performed or not. So this is a very quick walk through the paper. So thank you very much, and please let me know if you have questions.